Hello everybody. In this video, I'm going to go over some physics concepts within the context of calculus. Physics is the easiest concept to help explain the derivative as a rate of change. So in this video, I'll be talking about things like position, velocity, and acceleration functions, average versus instantaneous velocity, as well as having some examples of all of the above. Let's get into it. On this slide, I will be going over the position, velocity, and acceleration functions. First, some notation. The position function in physics and in calculus will be represented by either s or s of t. The velocity function will be v of t or v, and the acceleration function will be a or a of t. Now, within a mathematical sense, these three functions are related to one another. You can find the velocity function if you take the derivative of the position function. And very similarly, you can find the acceleration function if you take the derivative of the velocity function. We can also write the acceleration function just a little bit differently. Since we're able to write the velocity function in terms of the position function, we can write this velocity function in terms of the position function. If I took the derivative of the left side and right side of this equation, the derivative of the velocity would also be equal to the second derivative of the position function. So if you're given position, we can find velocity by taking the derivative, and we can find the acceleration by taking the second derivative. One other thing before I move on to the next slide, I want to make sure to point out that this velocity function that you see in front of you, this v of t, this derivative of the position function, represents the instantaneous velocity. On this slide, I'm going to go over the difference between instantaneous and average velocity. As mentioned on the previous slide, you can find the instantaneous velocity by first taking the derivative of the position function, and then in a lot of cases, you'll be given a value for time to substitute into the velocity function to find a velocity at a single time value. On the other hand, the average velocity is calculated over an interval of time, say from time A to time B. And because of that difference, the time being over an interval instead of a single time value, we have to use a slightly different expression to figure out the average velocity. In this case, we still use the position function to figure out the velocity, just like we did over here. It just looks a little bit different. We have the position at time B, which is the later time, minus the position at time A, which is the earlier time, all over how long the time interval was, B minus A. And one last thing before I move on to the next slide here is I want to point out that since the entire numerator here is about positioning, what we end up interpreting this as is the ending position minus the beginning position. And the word we use to represent this is displacement. How far are you from your beginning position? To get the idea across of the difference between instantaneous and average velocity, I just want to take a look at this example really quickly. Don't laugh at the art skills. So I live in the Houston area and I want to go to Las Vegas. So in average velocity, would be taking out how far did I fly divided by how long did that flight take, which is the average velocity idea in the previous slide. So I can tell you it is roughly 750-mile flight from Houston to Las Vegas, and it takes roughly 3 hours. And yes, these are rounded to make the numbers nice. So 750 miles divided by 3 hours would mean the average velocity is about 250 miles per hour. Now, the actual flight at any given time might have a different speed than 250 miles per hour. This is an average velocity over these 3 hours. You do not start with a plane on the runway instantly jumping up to 250 miles per hour. When a plane is on a runway, it starts out at 0 miles per hour before it takes off, right? From there, the engines throttle on, and about 30 seconds later, on average, the plane is just starting to lift off the ground. So maybe the front wheels are off. There we go. And at that time, 30 seconds into the flight, the plane is going about 160 miles per hour. And this is the difference in pictures, or in maybe the real world, the difference between an average velocity and an instantaneous velocity. An average velocity considers the entire trip. It took 3 hours to go from here to here, and it was this many miles, so 250 miles per hour. Whereas with the instantaneous velocity, we look at a very specific point in time during that flight. At time 0, we're sitting still. It's 0 miles per hour. 30 seconds later, we're starting to take off from the actual Earth, 160 miles per hour at that one point in time. In this slide, I'm going to go over an example on how to find the displacement, the average velocity, and the instantaneous velocity at a given time. So, for starters, we have a position function here, s of t equals 2t squared minus 5t minus 3. And we're considering this function on time 0 to time 13. And normally we'll have a units here, but I'm just going to assume that they're all seconds. So the first thing I want to do is find the displacement. And really, the displacement is just the numerator of the average velocity expression from a couple slides ago. So remember, that would be s of b minus s of a, where this is a and this is b. Remember, a is the beginning time or the earlier time, and b is the ending time or the later time. So we'll have an s of 13 here and an s of 0 second. So really, at this point, all we have to do is substitute 13 in for t here and here, because that's the position function, that's what we're trying to do. And then we would have to substitute 0 in here and here for t, and we would get the following values. 270 for s of 13, and -3 for s of 0. From here, we just have to compute this simple calculation to be 273, and I didn't give any distance units here, but I'm just going to assume they are meters. So 273 meters is the displacement from the starting position to the ending position. And this makes sense. If you start 3 meters behind 0, you have to walk 3 meters to get to 0, and then 270 more meters to get to 270. So 3 and 270, 273 meters. Next, I want to find the average velocity from the time 0 to 13. In order to do that, we will need to find S of B minus S of A, which we've already done here, so I'm not going to worry about this calculation too much. All divided by B minus A, which again are going to be times. .769 meters per second. And then if you need to, you can round that to any decimal place that makes the most sense for the situation you're in. Finally, we have this last one down here. Find the instantaneous velocity when t equals 6. I want to change that answer to 1, when t equals 1. So in order to find the instantaneous velocity at a specific time value, what needs to happen is you need to find the derivative of the position function. And since we have access to the power rule now, we can go ahead and use the power rule to find the velocity function of 4t minus 5. All right. So if we substitute 1 in for t, we will get the instantaneous velocity at 1 second. So what does that look like? We just substitute 1 in there. 4 times 1 minus 5 is -1. And that's it, -1 meters per second. So -1 meters per second means, in the easiest sense of understanding, is that you're moving backward at 1 meter per second. So you're moving backward 1 meter every second. This is different from speed. And I wanted a negative value so I could talk about speed. So -1 meters per second is a velocity. A speed is the absolute value of a given velocity. So let's see here. The absolute value of velocity equals speed. So we can talk about velocity having specific signs, either positive or negative, meaning moving forward or moving backward. Or we can talk about the speed. So even though this object is moving backward 1 meter per second, the speed of this object is 1 meter per second. Moving on with some more examples, we have a new position function, and I haven't given you an interval of time because I'm not worried about average velocity on this slide. What instead we're worried about is noticing that I'm asking for velocity at a specific time. So that means we will be finding the derivative, and that this is also an instantaneous velocity. And we have access to the power rule, and to find the instantaneous velocity function, we just use the power rule to take the derivative of this function here. So the instantaneous velocity function will be v of t equals 3t squared minus 8t plus 4. And with that, we can then substitute the time value of 3 in for t everywhere in this function and simplify to get the instantaneous velocity. So when you substitute 3 in here for t, you get 3 times 3 squared minus 8 times 3 plus 4. 3 times 3 squared is 27. 27 minus 8 times 3 is 24. 27 minus 24 is 3. 3 plus 4 is 7. And again, in most physics texts, you talk about meters and seconds for the units of measure of distance and time. So We're just going to stick with that for now. So 7 meters per second. Now, moving on, we have a completely new way of thinking about the velocity function. Now we're trying to find times when the velocity is 0. And again, when we are talking about a 0 velocity, we're not talking about an average velocity. I don't think a 0 average velocity doesn't make a whole lot of sense. So what we're doing is we're looking at an instantaneous velocity. And in order to find that instantaneous velocity, we need the instantaneous velocity function, which we already found back here in this step. So what we have to do now is we have to recognize that we are trying to find times, which means we will not be substituting a number in for t, but we do know the velocity is 0, which is this entire variable here. The velocity is v. So we can set up an equation that looks something like this. 0 equals 3t squared minus 8t plus 4, and we can solve this for t. You can use either factoring if it factors, or the other common quadratic solution technique is the quadratic formula. Thankfully, this factors, so we can say 0 equals 3t minus 2 times t minus 2, which gives us then 2 times, if you set each factor equal to 0 and solve for t, you'll get t equals 2/3, and t will also equal 2. So at these 2 times, we will have a velocity of 0. The last example on this slide here, you can see we're trying to figure out the acceleration at time 2. And for this, we have to actually first find the acceleration function, which is the derivative of the velocity function up here. And again, we can just use the power rule. We can say the acceleration function, I'm going to call it a of t, equals 6t minus 8. And once you substitute 2 in for t, you get a of 2. That is 6 times 2 minus 8, which is 12 minus 8, which is 4. And the units here are meters per second squared. A couple more things here. Back in this example where we're trying to find the times when the velocity is 0, these are both in the units of seconds, and I just want to put a box around this first answer here. And one last example for this video. I'm giving an equation for a position of an object being dropped from a 450-foot building. T is in seconds and S is in feet this time. The first thing I want to do is find the velocity, speed, and acceleration functions. This might be asked of you in many different ways, not limited to finding the velocity, speed, and acceleration at time t. So we can just go ahead and move over to the velocity function by taking the derivative. And it looks like the velocity function will just be negative 32t. Remember, the derivative of a constant is just 0, and we would use the power rule here. The acceleration function, which I think would be the next easiest one to answer, would just be the derivative of the velocity function, so just negative 32. And the speed function will absolutely be the absolute value of negative 32t. So no matter what time value you're given, the speed will be a positive number, because that's what speed is. It's the positive value of the velocity. Another question that could be asked in this scenario is how long before the object hits the ground. And in order to figure that out, you have to recognize that you're finding a value for t. But you can also recognize that hitting the ground means the height or the position isn't 450 feet above the ground anymore when you dropped it, but it is 0. The position is 0 because it hits the ground. So the position would be 0. Oops, there we go. And we would be solving for time. So you can subtract 450 from both sides. Then you can divide both sides by negative 16. So a negative divided by a negative would give you a positive. And then you could take the square root of both sides, but then realizing that taking the square root of both sides would give you a plus or minus in front of the square root of the number, and recognize that time cannot be negative. So we would just leave it as the positive value of 450 over 16 seconds. And that is what t will equal here. But again, as with a previous example in this video, you don't walk around and say, hey, how long would it take for, and someone actually respond with square root of 450 over 16 seconds. Duh. So I'm going to change this into an understandable number, which is 5.303, and with a ton more decimal places after that, seconds. So what you want to keep in mind is, again, whenever you're looking at decimal answers, just be aware of what's being asked of you, which place you're supposed to round to. Let's see, I do have one more thing I want to look at here, and that is the question, how fast was the object moving at the moment of impact? Now that could take one of two meanings. How fast could mean velocity, and how fast could mean speed. So recalling the two equations I have from the last slide, I know that the velocity equation was negative 32t, and the speed equation was just going to be the absolute value of that. So all we have to do is take this 5.303 seconds, or if you want to be very exact about it, you can use the square root and substitute it in for t here, and that will give you the velocity. Then all we have to do is take the absolute value of that, and we will have the speed. So when you substitute this value in for t here, you get negative 169.706, and since our units are listed at the top there, this will be feet per second. And then the speed, of course, will just be, let me write, speed will just be 169.706 feet per second. And I used, just for clarification, I used the exact value here to figure this out. If you use a rounded value, it is slightly different. The decimal becomes 0.696. So just be aware of that. If you're getting an answer wrong at some point, it's because of the rounding error here. And that will conclude it for this video. I hope this video helps you out, and I'll see you in the next one.